Okay, before talking about the latter part of the chapter 3, Shin Min-jun has requested how to count degree of freedom of this robot system. Okay, to begin with, let's combine all the joints in the leg. So this will be considered as a one joint. Okay, it has the many degree of freedom. Like this, we have the 1, 2, 3, 4 leg as a joint. And then the ground will be considered as a link. The first link has the 4 joint supported by the joint, and then we have upper plate. So number of the link will be the 2, 1 and 2. Joint will be the number of the leg, so we have the 4. The remaining problem is to how to count the Fi. Okay, 4 times we have the 4 leg. Okay, let's count the number of the joint in the leg. Okay, the 4-bar linkage has the 1 degree of freedom. And then let's consider the bottom part of the joint here. It is connected using the 3 link. According to the definition of the joint connected only 2 link. It implies this level of joint must be the overlapping joint using the 2 level of joint. So it has the 1 degree of freedom, and the POVA has the 1 degree of freedom. In here, this is connected to 3 link, 1, 2, 3. It means it is overlapping joint. So one more level of joint here, 1 degree of freedom. And the level load and the prismatic and the level load. Let's all count it together. 1, 2, 2, 3, 4, 5, 6. So each leg has the 6 degree of freedom. It results in the 24. Let's apply the globular formula using this data. Okay, the 6 times n minus 1 minus j plus sum of degree of freedom of the joint. So 6 times 2 minus 1 minus 4 plus 24. So we have 6. It has a 6 degree of freedom. If you have any questions, email me including the number of the exercise. Okay, let's consider the section 3.3, the rigid body motion. Later will be extended to the twist concept. Twist is the rigid body velocity in viewpoint of the screw axis. Okay, in the previous lecture, we have talked about the rotation and the angular velocity using the exponential coordinate for rotation. Actually, this is the rotation axis, and the rotation angle theta. By taking a time derivative of theta, we defined the angular velocity using the rotation axis and the angular velocity as a scalar. This kind of concept will be extended to the rigid body motion. In order to describe the rigid body motion, we have the 6 elements, such as the 3 rotation and the 3 translation. But in order to describe the rigid body motion, we will introduce the homogeneous transformation. This is the matrix composed of 4 times 4 elements, analogous to the rotation matrix. The way to describe the rigid body motion is to use the 6 elements, but we will use the 4x4 16 element matrix. To extract the necessary element of a homogeneous transformation, that will be the square axis belonging to R6. This is very similar concept to the rotation axis. On the other hand, the twist, square axis times angular velocity, will be defined similar to the angular velocity for the rotation. Finally, the exponential coordinate as theta belonging to R6 will be described for the rigid body motion. Okay, so the previous concept, the exponential coordinate and the rotation axis, will be extended to square axis and exponential coordinate for the rigid body motion. Furthermore, the angular velocity is extended to the twist later. Okay, maybe you are good at the homogeneous transformation. Anyway, I will explain it in detail. Okay, the homogeneous transformation is used for orientation and the position of a rigid body. Okay, actually, the natural choice would be to use the rotation matrix to represent orientation of a rigid body, frame B, in the fixed frame S. The core element is the 3, but we are using the rotation matrix as a 3 by 3, using the 9 element. And vector belonging to R3 is required to represent the origin of the B in S. Okay, like this, rotation matrix and the vector P can be used for obtaining the rigid body motion. In here, in these lectures, we will combine the both kind of concept. So we will package them, rotation matrix and the position vector, into a single matrix using a homogeneous transformation. Sometimes a single matrix T will be denoted by the R and P. Okay, those are saying each other. Okay, the special Euclidean group denoted by the SE3 is known as the group. Group is the mathematical group of rigid body motion or homogeneous transformation in R3. But SE3 using the 16 element because it has the 4x4 matrix. So the SE3 is the set of the all 4x4 real matrix T of the form. So 3 by 3 rotation is here, and the 3 by 1 vector is here, and the 3 zeros, and then 1 will be appended to make the 4 by 1 matrix. Okay. In the previous lectures, R belongs to SO3. SO3 has the many good property to manipulate the matrix. The P belongs to R3 as a column vector. As a special case, the special Euclidean group denoted by the SE2 is the set of all 3 by 3 real matrix T in the planar case. So rotation matrix will be the 2 by 2, and the position vector will be denoted by the 2 by 1. So 2 zeros are required, and 1 will be added to here to make the 3 by 3 matrix. Maybe you are good at this kind of a rotation matrix in the high school. Okay. Similar to the rotation matrix, the homogeneous transformation has the similar property with the rotation matrix. Okay, in the previous lectures, SO3, not SE3, SO3 belongs to group, make the group, is it right? In order to be the group, mathematical group, we need 4 property. First, all the operations should be closed. Multiplication should be remained in the same set. The second, it has the identity. third one, it has the inverse. On the other hand, it has associative property, not commutative. So this kind of four properties are achieved, then we can make the mathematical group. This is about the SO3. This concept is extended to the SE3. Okay, so SE3 is also a mathematical group. So it means it has identity. Maybe you know the identity matrix as a 4x4. So one of the four properties are achieved already. And then inverse exists. Inverse of transformation T, also transformation. So the set is closed. In the case of the inverse, it has the following form. Okay, the T is given R and P 3, 0, and 1. Okay, let's write down the inverse, generalize the inverse. Okay, let's consider Bloch matrix A exists, B, and 0 matrix, and C. At that time, the inverse will be achieved, can be obtained. A inverse minus A inverse B, and C inverse, and 0 C inverse. This is the Bloch matrix inversion of a 2x2. Okay, let's apply this one. Okay, R inverse is this part, and minus R inverse B, and 1 inverse is the 1. So minus R transpose P is this one, and 0 and 1. So this matrix belongs to SE3 as well. On the other hand, the product of two transformation matrices is also a transformation. So set is closed. And the multiplication of transformation matrices are associative. So this kind of associative property is achieved, not commutative. So including the identity matrix, we can say that four properties are achieved. Four properties are conducted in this set, in this matrix set. So the SE3 must be the mathematical group. Okay, maybe you know the vector has the 3 elements, but we will add 1 to the last element. Like this, 3 elements, and 1 is added, 1 is appended to here. So we can make the 4-dimensional vector. This is called as a homogeneous coordinate. Homogeneous coordinate has the 4 elements. The last element always 1. If you add the 1 like this, then we can make the matrix vector multiplication because the T has the 4x4. So let's calculate. T has the RP01, then x1 will be applied to here. Then we have the Rx plus P, and then 1. Actually, this 1 implies the homogeneous coordinate. So the result will be the Tx is considered as Rx plus P. Okay. Actually, this is the overuse of notation because the x has the 3 element, but Tx, in the case of the Tx, x has the 4 element as a homogeneous coordinate. Okay, we will allow this kind of overuse of notation here. Okay, for given T described as R and P belonging to the SE3 mathematical group, special Euclidean group, and for given x and y belonging to R3, at that time the following elements are following elements are satisfied. Okay, transformed the subtraction will be equal to the original subtraction. It means the transformation does not affect any distance variation. On the other hand, inner product will be denoted by the bracket like this. The same way, the transformed inner product will be the original product. So the transformation T preserves distance and T preserves angle because the inner product is the same and the distance is magnitude is the same. From here, we can know that the transformation preserves distance as well as the angle. So if you take the three elements to make the triangle, x, y, and g, okay, let's assume that this is a tx, this is a ty, this is a tz. At that time, the length will be the same, angle will be the same, because the transformation preserves angle and distance. So we have the same triangle. Actually, this is a displaced version of the original triangle. So taking x, y, and z to be the point on the rigid body, and the transformed tx, ty, tz represent the displaced version of the rigid body. So using this kind of concept, the SE3 can be used to describe the rigid body motion. Similar to the orientation matrix property, the transformation matrix can be used to represent the configuration. On the other hand, it can be used to change the reference frame or to displace the vector warframe as an operator. Okay, the homogeneous transformation can be used to represent the configuration as mentioned before. Okay, let's assume that we have the physical point V here. In order to describe the position of the V, we will attach the coordinate frame like this, x and y and z. It can be used as a fixed coordinate to describe another one. Okay, at that time we can define the point V. But the coordinate value is dependent on the coordinate axis location. So if we attach another coordinate here, x and y and z, denoted by the B frame, at that time the coordinate value will be different. Is it right? On the other hand, if we attach another base frame like this, x and y and z, at that time we have another coordinate value of the point V. Like this, we can use the transformation matrix to represent the coordinate or configuration. Okay, this is example. A frame is equal to the S here. This is the assumption of this one. Okay, and then let's describe the B frame in terms of the A frame. So x vector will be the g vector, so 0, 0, 1. And the y vector will be the minus y, so 0, minus 1, 0. And then g vector is equal to the x, so 1, 0, 0. Okay, like this we can read the configuration of a frame. Okay, let's assume that this coordinate value, coordinate of the origin of B frame in terms of the A. Okay, let's assume that this is a 2 unit in the minus y direction. So 0, minus 2, 0. Okay, let's apply this kind of concept to the base frame C. X can be read using the minus x, so minus 1, 0, 0. And the y is the g, so 1, 1, 0, 0, 0, 1. And the gx is the y, so 0, 1, 0. And then the minus 1x plus 1y, so minus 1 plus 1, 0. Okay, like this, we can read the origin of any frame with respect to another frame. For example, let's read the RBC. C frame can be read using the B frame. Okay, how about that? X is equal to the minus Z, so 0, 0, minus 1. Y is equal to X, so 1, 0, 0. And then Z is equal to minus Y, so 0, minus 1, 0. Okay, maybe the origin of C frame can be read using the B frame. Here is the 1, 1, 1, minus Y direction, and then minus G directions, minus 1. So 0, minus 3, minus 1. Like this, we can describe the origin or frame using another frame. On the other hand, TCB is equal to minus TBCE matrix inverse. Like this, we can exchange the coordinate frame. Okay, similar to the cancellation dual or subscript cancellation dual, this concept is applied to the homogeneous transformation. Okay, TAB multiplication of TBC. Okay, this B, both B are cancel out each other, then we will have the TAC. So the frame of the C can be described in terms of the frame A. Okay. On the other hand, the VB implies the vector V expressed in the B frame. Okay, if we multiply the TAB in front side, then we will using the cancel subscript cancellation rule, we have the VA. It is equal to the vector V expressed in the frame A. Like this, we can change the base frame. The third property is that transformation matrix can be used to displace a vector and the frame. Okay, the transformation matrix viewed as a pair of R and P. Okay, in order to emphasize R matrix as an operator, we can write down lot omega axis, theta angle, and then P translation. This RP can act on the frame TSB by rotating it by theta about the axis omega hat and translating it by P. Okay, this interpretation is about operator function of a transformation. Okay, let's extend the 3x3 rotation matrix into the 4x4 homogeneous matrix. Okay, so let's introduce the rotate operator. Okay, the rotation matrix R is here, and the remaining last column and the last row can be occupied 0, 0, 0, and 1. Okay, to make the 4x4 matrix. But it acts like rotation matrix in 4x4 element SE3. Okay. In order to describe the translation motion of without rotation, we can make the SE3 operator translate P. Actually, this 3 element is about the translation function, but we will add identity matrix and the 3, 0, and 1. Like this, we can make the SE3 operator for translation without rotation. Okay, in here we will talk about the pre-multiplication and the post-multiplication will bring the very different result as operator function. Okay, if we multiply the transformation matrix T in front side, okay, it is corresponding to the pre-multiplication by the T matrix. Okay, in this case, the transformation is act like the translation and rotation, so we will extend the function of T matrix, okay, using the SE3 region. Okay, and here's the pre-multiplication implies all the operation is achieved in the S frame, fixed frame. So TSB representation can be changed using this rotation first, and then translation is achieved. So free multiplication brings the result that the first rotating the P frame by the theta about the axis omega hat in the S frame, and then translating it by P vector in the S frame. Okay, we should mark in mind pre-multiplication will bring all the transformation achieved in the fixed frame, S frame. Okay, this is the result. On the other hand, if you multiply the transformation matrix in the lateral side like this, okay, it acts like the translation and rotation in the SE3. So in this case, the B frame is used. So all the operation is achieved in the body frame. Okay, this is the first translation first in the B frame. Maybe the B frame is the part is moved to the new frame. In the new body frame, the rotation is achieved. The sequence is very important. The translation first, and then rotation is later. On the other hand, in the previous pre-multiplication, rotation first and the translation later. Okay, this is the similar property with the rotation matrix. In the previous lectures, this is the operator of rotation. If you apply the two front side, at that times, rotation of the RSB is achieved in the fixed frame. On the other hand, the post multiplication of the R will be achieved in the body frame. Those are very similar concepts. Okay, let's take the example. Here, the fixed frame and the body frame transformation corresponding to this is the rotation axis 001, G axis. Rotation angle will be the 90-degree, and the translation is achieved in the Y direction, 2 unit. Is it right? Okay, let's take the example. This is the S frame. Okay, here, the body frames here, the 2 unit okay, this is the 2 unit. Okay. Okay, let's make the rotation matrix first. Okay, the rotation matrix, rotation angle or rotation axis is 001. It means okay, let's take this is the x-axis, this is the y-axis, this is the g-axis. Okay, the rotation angle will be the 90-degree with respect to the z-axis. So 90-degree rotation, then we have this rotated frame. You're right. G is the same. Okay, from here we can write down the rotation matrix. Okay, this is a new one. The x half prime can be read using the y. So we have the 0, 1, 0. The second column will be the minus y hat is equal to minus x. So minus 1, 0, 0. And then gx is the same, each other. So 0, 0, 1. I'm sorry. Okay. And then So P is the 0, 2, 0, and then the remaining 3 zeros are located here, and then 1 is appended here to make the 4x4 matrix. Like this, we can make the 4x4 matrix. This is the same. This one. Okay? This rotation matrix, the P, and the 0, 0, 0, 1. Okay? This will act like an operator of the TSB. Okay, let's read the TSB. Okay. Okay, I need the blank page to write down something. Okay. Okay, let's read the TSB. The B frame x-axis can be read using the minus G frame, so 0, 0, 1. And y can be read minus y-axis, so 0, minus 1, 0. Z is the aligned with the x-axis, so 1, 0, 0. And then this is a 2 unit minus y direction, so 0, minus 2, 0, and the 3 zeros and 1 as added. Okay, this is the operator. This is the representation. Okay, let's multiply this T matrix front side and lateral side. Okay, first let's obtain the pre-multiplication of T. As mentioned before, can be write down the two operators, translation and the rotation. This is the post-multiplication of the T. This is also can be interpreted using the translation and the rotation. And then we will take the frame. Here, S frame is the main. So all the operation is achieved in the S frame, fixed frame. So first rotation, 90 degree in the axis of the G of the S frame. So the G axis is chosen as a rotation axis, and then 90 degree is applied. So this B frame can be rotated to here. Okay. And then the translation will be applied. Okay, translation, the axis is the Y using the 2 unit. So we take the y-axis and then 2 unit is applied. So we have the final description of the transformation. Okay, we can check the correctness of this transformation. Let's lead the x-axis using the G, so 0, 0, 1. The y-axis is aligned with the x-axis, so 1, 1, 1, 0, 0. And the z-axis is aligned to y, 0, 1, 0. This is the 2 unit x-axis, the 2 unit y-axis, so 0, 2, 2 zeros. And then we will add the 3 0 and the 1 is appended to make the 4x4 matrix. Like this, we can interpret the pre-multiplication of the transformation as an operator. On the other hand, if you consider the post-multiplication of the T, the same is applied. Okay, in here we take the body frame, the first translation. Maybe applying this operation, we can get a new body frame, and then new body frame can be used to apply the rotation. This is the second part. Okay. Okay, the y direction 2 unit is required to achieve the P translation. So this is the P frame origin, and the 2 unit going forward is required. Okay, according to this translation. So this frame is going forward 2 unit, and then we have the new body frame here. Okay, orientation is aligned with the B frame, and then we will take the orientation in the G direction. Here, G direction is like here, and then we take the 90-degree orientation. So the x-axis will be rotated here, and the y-axis will be rotated to here. Okay, let's read the final orientation in terms of the S. Okay, in here, x-axis will be led minus y, so 0, -1, 0. And the y-axis is aligned with the minus z, so 0, 0, -1. And the z is aligned x-axis 1, 0, 0. And then 2 units going forward, and then 2 units more going forward. So we have the minus 0, -4, 0, 3, 0, and 1. Okay, you should memorize the difference between the pre-multiplication and the post-multiplication. Okay, let's take the example one more. The final target is to pick up the object using the robot arm. Okay, to achieve this kind of task, we will attach the many coordinate frame. Okay, here the base frame or reference frame or fixed frame is attached to here, denoted by the A. This is a camera. Camera has the D frame. Maybe after you are installing the camera, and then we can get the TAD. It's very easy to obtain it using the rotation and the translation. And robot will move in the ground. So let's attach the body frame B and attach the coordinate frame C in the end effect of the robot arm. And the object has the E coordinate frame. Okay, the camera will provide these two transformation. Is it right? Camera will detect the image, and then we can calculate the transformation matrix from the TDE and the TDP using the camera. Okay, here the final target is how to obtain the TCE. Okay. In order to obtain this transformation, let's apply the loop system. Okay, TAB and TBC and TCE can be used to obtain the transformation. Okay, maybe the TAB times TBC and TCE will make the TAE. Okay, is right? Maybe the TBC can be obtained using the kinematics. Will be learned next topic, next week. And then TAB, it's very difficult problem to obtain it. So TAB can be achieved using the indirect way. We know the TAD and the camera will detect the TPD. So TAT and the TDP. The available information of these two transformations, we can get the TAB. On the other hand, using the camera, we can detect the object position and the posture. So TAD and TDE can be achieved using the camera, TAD and TDE. We know that all the elements, but we don't know TCE. So TCE can be obtained using this kind of a multiplication or inverse. Like this, we can assign the robotic task using the homogeneous